Hello, everybody. David, thank you very much for the introduction. My name is John Morgan. I am a solution development engineer with Enervex. I focus primarily on energy conservation. Two main areas are demand control, response ventilation, and waste heat recovery. So this is a fairly technical presentation. I'm an engineer, so I want to apologize up front. I'm going to try and keep this as simple as possible and try to keep it to the 10 minutes that I have been allotted. So like David said, we met last year at the AHR conference. He was very intrigued with the kind of energy work that I do here at Enervex, and he and I have been working together basically ever since on some energy recovery projects, several of them here in Canada. So I always like to start with this graph, just because, like I said, I'm an engineer and this is a slightly technical presentation. This is just a boiling graph of water. And for a long, long time, condensation, especially in gas combustion systems, propane systems, was a very dirty word. We didn't want to condense. We didn't want to have to use the materials required that would, stand up to that kind of environment. The different flues and chimneys that we were using, whether they were stone or otherwise, also could not handle condensating environments. But what I want to illustrate in this graph here is the amount of energy that is available to us after the water has actually evaporated and changed phase. Many, many times, this is the energy that I'm going after in a waste heat recovery project. I want to get my flue temperatures, my exhaust temperatures, as low as I possibly can. Now, in some instances, that is a big problem. The existing flue system may not be able to handle it. Maybe it's a type B vent or some kind of galvanized metal that is not going to withstand corrosive environments. There are ways to get around that and still be able to implement waste heat recovery systems. I'm not sure if I'll actually get to that in this presentation, but there are things that you can do to get around that. But what I wanted to illustrate here, this flat line is what we're going after most of the time. We want to get as much of that water condensed out of the flue stream as we possibly can. So a lot of the projects that I'm working on fall within hospitals, multifamily, higher education, at least in the commercial world. The key energy sinks and efficiency targets that I go after usually fall into the domestic hot water systems, steam, recirc lines. Definitely winter heating air is a big one, especially in my region. I'm in New England. We have very, very cold design days. Definitely makeup water is also another key target. So if you're bringing in a lot of outside city water, there's usually a fair amount of opportunity to preheat or totally heat that with waste streams inside of your facility. At least in my region, absorption chillers are also fairly common. Sorry, I'm not as educated on Canada if you guys see them as often as I do. But usually what happens is a higher education facility builds a dorm room. They want to be able to cool it, so they want to put in a 500-ton air-cooled chiller. They contact their electric utility and ask, how much capacity do I have left? And they say, none. You cannot put that in. So that drives them to their gas utility, and they ask them, how much capacity do I have? And they say, you have enough. You can put in a dedicated heating system, and you can use that to drive your absorption chiller to be able to provide a cooling cycle for your new building. Then on the modulated building exhaust side, the demand control response side of it, I work in a lot of central kitchens, bathrooms, and laundry systems. So multifamily applications, multi-story buildings where the domiciles are very, very similar in layout, and maybe your laundry systems are all stacked on top of each other, pulled over to a central trunk line with a fan on the roof, systems like that. Now, in the industrial world, a lot of the projects that I see go into some kind of food processing. So we're talking bottling plants, we're talking bakeries, anybody making a cookie or a pizza. Definitely breweries are a big topic. They use a lot of steam systems that tend to have a lot of waste heat coming out of their chimneys. But we also see lots of ovens and furnaces. We're talking metal treatment facilities. We're talking annealers. We're talking operators of thermal oxidizers and blast furnaces for large groups like Prime Metals or Nucor Steel. A lot of the energy sinks and efficiency targets are pretty similar to the commercial world, from the domestic water on down through the absorption chillers. But in the industrial world, I start to see some things that I don't really see in the commercial world, such as air compressor cooling. It is getting less and less, but there are a lot of industrial facilities out there that have pneumatic control systems, all right? So I've had at least 2 or 3 engineers contact me in the past 4 months asking me, what can I do with all of this exhaust heat that I'm throwing away from my air compressors? I have to pass a lot of air over them to keep them cool. Right now, I'm just rejecting it to the atmosphere. What can I use it for? So I'm helping them understand different loads within their facility, space heating or process, whatever the case is. Maybe they need to leverage a heat pump to increase that temperature differential. But then we also start to see 2 significant industrial applications of heat pumps that I do not see very often in the commercial world. The first is steam generating heat pumps. There are technologies available today that can do about 5 psi of steam generation using a water source heat pump technology. So a good example, I was working with a food processor recently. They focus on extracting essential oils from different things. One of their processes was mint leaves. They extracted mint oil from mint leaves by injecting steam into the system. They're currently using a gas-fired boiler to provide that steam load, that low-pressure steam load, to extract that mint oil, and they're under electrification initiatives. So they're looking for ways that they can electrify that load. So I'm helping them look at a waste heat recovery system to capture waste energy from another part of their processes, bring it into a steam generating water source heat pump to electrify that steam load for them. Then we also see what are called organic Rankine cycle thermal harvesters. These are basically an absorption chiller. However, instead of rejecting that heat to a cooling tower and providing a cooling loop, these use the phase change that the refrigerant goes through to drive a turbine. So you can generate on-site electricity. I will say that for ORCs, only place I've seen them really applicable is the largest industrial users of energy. We're talking prime metals, Nucor steels. We're talking about those groups operating very large blast furnaces and thermal oxidizers. A very good example was a coal mine in the mountains of Pennsylvania I was working with recently. They have a very remote site, like I said, up in the mountains. They don't have the best or reliable utility service, water, gas, electricity. So they're looking for ways to make their facility more resilient and more redundant. They operate a very large thermal oxidizer, burning hundreds of thousands of CFM at about 1,400 degrees Fahrenheit. Now, I know you guys are in Celsius, but you can make that conversion. Either way, that's a lot of energy. 1,400 degrees Fahrenheit is a lot of energy. So what this group is looking to do is harvest waste energy, heat energy out of that thermal oxidizer, feed it into the ORC machines to generate roughly 3 megawatts of on-site electricity for themselves. These are very, very resilient machines. These are not heat recovery steam generators that require a clean source of water. They are completely enclosed, and for an application like this in the remote areas of the mountains, it can make a really, really big difference for them. Then on the electric side, the demand control response side, I still see lots of bathrooms and laundry systems in industrial applications, especially those groups that have their own uniforms and their own washing facilities for those uniforms. And then we see a whole lot more of those ovens and furnaces in the industrial world than we see in the commercial world. So we're going to start things off. This is actually a case study that we did with Enbridge Gas and the Natural Gas Technology Center here in Canada. So this was a large multifamily application that had an existing constant speed exhaust system for their central laundry, all right? So each floor is stacked on top of each other. This was a 3-story building, and each one of the domiciles was basically a mirror of the one below it. So each one of the appliances is pulled over to a central trunk line, and all of the exhaust is performed by a central fan located on the roof. So the red graph on the left-hand side, your left-hand side, is the existing constant speed system that they have. Code says that we can't turn the system off, right? Code doesn't say that we can't ramp it down, though. So what we showed them that could be done is we can replace that constant speed system with a demand control response system, and we can significantly reduce the amount of fan energy that you require and the amount of exhausted air coming out of your domiciles. This is air that we have conditioned. We have spent money and energy, make it warm, make it cool, humidify, dehumidify, whatever. We've spent money and energy to make this air in these spaces comfortable for these people. Needlessly drawing it out of the building with a constant speed system is just a waste of energy. So the green graph is pretty straightforward. Once we replaced the system, we measured it for about a year, put this case study together, and I can share that case study with anybody who would like it. But we came up with the usage graph on the right. As you can see, everybody's running their appliances first thing in the morning and very last thing in the afternoon. The other 75, 80% of the day, there's just no need for that fan to be operating at its maximum. We don't need to use the electrical energy, and we don't need to exhaust that conditioned air out of our spaces. So to give you a quick idea of magnitude, this entire project for this multi-story building was about $60,000 installed. That was that's the contractor, the labor, the parts, the pieces, the equipment, everything. After we were done with the case study and we did all of the calculus and we did all of those nitty-gritty calculations to try and come up with an idea of how much air we weren't taking out of our spaces and how much energy it took to do whatever we wanted to that air, and then how much we were no longer using in our fan energy, it was about $77,000 a year in savings. This project had an 8-month payback for this site owner. Anytime I am in a building and I'm consulting on energy conservation measures, this is always something that I'm looking for. If they are operating any kind of exhaust system, especially for applications like this, I'm always looking at DCR as a meaningful way to save a lot of energy for them. There are rebates, there are incentive programs dedicated to these kinds of projects. There is money out there to get them done. Okay, we're going to talk about runaround loops. How much time do I got, David? Okay, I'm going to try and quickly run through a runaround loop, all right? This is a very, very simple concept, but a very, very powerful one in the engineering world. And the idea is to simply capture energy out of a source that you are exhausting to the atmosphere and pull it over into the place that you are trying, or where you need to use the energy. For this particular example, this is a building that is under GEDO right now. They have kind of two main problems. One is GEDO. They're going to be hit with fines very soon if they don't find a way to reduce their carbon output. And they're also at risk of putting people in hotels because on the coldest days of the year, they can't keep their domiciles at temperature. They've got about 30,000 CFM of building exhaust coming out of their kitchens and bathrooms. So they got about 30,000 coming in from a makeup air unit. That makeup air unit is not able to temper that air up to 70 degrees during the coldest parts of the year. So GEDO, they're going to get hit with fines soon because they're putting out too much carbon according to the regulations. And they might have to put people in hotels because they can't keep their domiciles warm enough. So what I'm helping this engineer do is work on two main energy recovery systems. The first is this runaround loop to leverage a water source heat pump to run a chilled glycol loop through exchangers located in the exhaust ducts and pull all that energy that we can over to the makeup air unit. Now, this is roughly 70 degrees of building exhaust air. So we're not talking 50 degrees outside air. The COP on a system like this is very, very good because we're able to operate at a higher ambient temperature. Now, this is a pretty expensive, pretty complicated system. Don't get me wrong, this is a great system, nothing wrong with it, but it's fairly expensive, it's fairly complicated. Just a water source heat pump alone is very, very expensive for a building of this size. So this is a value engineer option. This is the Enervex design that we have put in front of them. And what this centers around is their current water heating system. This is the system that is tapping out on the coldest design days, right? It's located in their basement. All of their flue is commonized into a single trunk line, and it penetrates from the basement, comes up through the building, and penetrates through the roof. What's located 20, 30 feet away in a penthouse? That makeup air unit that is running out of heat on those coldest design days. So, very complicated, great project, very expensive. This is much, much simpler. And this gets them all the way that they need to go. This gets them that 70 degrees of lift. This gets them waste heat recovery incentives and rebates available from the programs that are, existent, and is just a really, really good, solid way to do the system. This system is already tapping out. So on those coldest days, this system is running as hard as it can. And right now, under this last design, that makeup air unit cannot, there we go. Anyway, that makeup air unit just can't get there. This gets them all the way there. This is the last one that I'm going to talk about because this is a Canadian project. This is actually the project that he and I are working on right now. This is a farm with a large greenhouse. They currently operate 5 900 horsepower boilers and 4 cogenerators. All right, they are up for an expansion and they need to put in somewhere around 4 more 900 horsepower boilers and around 3 to 4 more cogenerations. So what we're helping them look at is ways to increase the overall capacity of their current system so that they can minimize the amount of capital investment that they need to make in new equipment. Basically, how can we increase the efficiency so we can buy them more horsepower out of their current system to minimize the new horsepower that they're going to have to purchase. So there's 2 systems that we're looking at right now for them. There's a 2 economizer setup. And what this does is this basically takes their roughly 86, 90-degree loop return, sends a portion of it through heat recovery economizers located in the exhaust stream, preheating that 86 degrees up to somewhere around 105 degrees at about 1,200 GPM of flow. So what that does for us is that gets us about 430 horsepower of additional capacity out of the system. Now, this can be stepped up, this can be staged, you can put in more economizers, you can increase the size of the economizer. It just all really depends on the system.